In 1905, Albert Einstein, a young and relatively unknown physicist, published a paper that forever changed our understanding of light and energy. His explanation of the photoelectric effect introduced the concept of photons and became a cornerstone of quantum mechanics, revolutionizing physics and paving the way for modern technology. At the time, scientists were baffled by a phenomenon observed when light struck certain metal surfaces, causing electrons to be ejected. Classical physics, which described light as a wave, predicted that increasing the brightness of light would increase the energy of the ejected electrons. But experiments revealed otherwise. Increasing brightness increased the number of ejected electrons, but didn't affect their energy. Surprisingly, the energy of the electrons depended on the light's frequency, or color, rather than its intensity. Even more puzzling, if the light's frequency was below a specific threshold, no electrons were emitted, regardless of how bright the light was. Einstein proposed a bold solution to this mystery. Light behaves not only as a wave, but also as though it is made up of discrete packets of energy, which he called photons. Each photon carries energy, and when one strikes a metal surface, it transfers that energy to an electron. If the photon's energy is high enough, it can eject the electron from the metal. The leftover energy determines the speed of the ejected electron. Einstein's explanation accounted for all the observations. Increasing brightness adds more photons, resulting in more ejected electrons. But the energy of each electron depends solely on the light's frequency. Higher frequency light, like ultraviolet, contains photons with enough energy to eject electrons at higher speeds. Meanwhile, lower frequency light, like red light, doesn't have enough energy to eject any electrons, regardless of its brightness. This revolutionary idea challenged the classical view of light and introduced the concept of wave-particle duality. Light exhibits both wave-like and particle-like behavior. This principle became one of the central ideas of quantum mechanics. Einstein's work on the photoelectric effect was so impactful that it earned him the Nobel Prize in Physics in 1921, marking a key turning point in the field. The practical implications of the photoelectric effect are enormous. It laid the foundation for technologies like solar panels, which convert sunlight into electricity, and photodetectors, which are essential in cameras and imaging devices. It also contributed to the development of quantum mechanics, which underpins technologies like semiconductors, lasers, and quantum computing. Einstein's explanation of the photoelectric effect wasn't just a breakthrough in physics, it was a paradigm shift. By challenging classical ideas and introducing the concept of quantized energy, he opened the door to a new understanding of the universe. From renewable energy innovations to the devices we use every day, the impact of this discovery continues to shape our world.